Okay, 2.9, that's not 9 fingers. 2.9. Linear approximations and differentials. And so that's what we're going to check out in this section here. And I remember that I said when we drew, we had a curve. There's the curve. And we had a tangent line. And I said, as I drew the tangent line on there, wow, this is almost exactly on the curve for a really long distance. Well, you can always kind of go in so that there is a place where the tangent line and the curve are about the same. And what that's called when you do that is called a linear approximation. And so that you're using this tangent line to approximate this curve. But it doesn't approximate this curve everywhere, but it does a pretty good job in a certain neighborhood. And so like from here to here-ish. And so from here, x1 to x2, that if I wanted to find out the value, the y value for the curve, that the y value that goes with the tangent line would be just as well, that the tangent line and the curve are nearly the same. So if I wanted to estimate the y value on this curve, I could use the y value from the line, from the L stands for the linear approximation, the tangent line. And this is the formula they give for the linear approximation, and they act like, hey, this is a new thing. Look at this formula. And I say, hey to you, isn't that just the tangent line? I mean, this is the fancy way that we're going to say y here, right? And this is the point. This is our y1 on the other side over there. Whoops, that should be plus y1, right? And minus y1 when we get it over there. And then the slope of our tangent line. And then x minus x1, right? And so really, and this was our, put that on the other side. It's just the tangent line. And so, yep. How do you spell yep? Yep, that's what it is. And so, so it's not anything that new. The idea that they're going to try to be honing in on, though, is that you can use L of x to approximate f of x. And so that's going to be kind of the big deal that they're going to be having. And yeah, if I ask you for the linear approximation, then this is the notation you should use. Even if you first have this, then you should change it into that, right? So that you tell people, that's how you tell people it's a linear approximation. So that's what they're asking us to find here. Find the linearization L of x. So the linear approximation, now they're saying linearization, meaning make the curve into a line, right? And check it out. I went outside just for a few seconds and I got bit by there were mosquitoes flying around, and I thought I could swoosh them off myself and sit on my front porch swing, and I've got like 6 bites, and I am not thrilled about it. Okay, so I'm going to stop complaining though, because complaining doesn't help. So I want to find the tangent line. So how you find the tangent line is you have to find the slope, right? And you have to find a point. So you need the slope of the tangent line, right? You need this, and you need to know a point. And actually, they're telling me the x-coordinate of this point, they're using A, and so, but I need to find the y-coordinate. Well, the y-coordinate is not hard, right? The y-coordinate is given by y equals f at x equals sine, right? And what is our x value? Pi over 6. So sine of pi over 6. And sine of pi over 6 is something that you should definitely know. And so that you should be able to say to yourself what it is. You shouldn't have to use a calculator to find it. You should be saying, oh, I know that one. That one's a friend. And so anyway, if it's not, you want to get them so that they are a friend. If they're already a friend to you, then I've already told you guys to write your trig teacher a letter. saying thank you. Okay, now the slope of the tangent line is y prime at this point, pi over 6. Or, so instead of saying y prime, I could say f prime at pi over 6. So I want to find that. So f prime, fortunately, is not very hard. The derivative of sine is just simply cosine. And I want to evaluate this at pi over 6. Pi over 6. So cosine of pi over 6. So just like the sine of pi over 6, you should be like, oh, I know that one. And so there we have that. Okay, so that's our slope. And so then our tangent line would look like y minus y1. You can use the notation of the book if you like on the linearization and plug in. And I don't, and it's fine. It works out okay. And so this is y equals, add the half to the other side. And if this made nice, if this was nice when I distributed it, like those were just regular numbers and not nasty numbers, like I kind of have the pi over 6, that's not too bad, but 6 is not very nicely printed, and I need to do better on my printing there. And so then you could distribute it. But you do need to say that this is L of x. So you need to, because you were asked for the linearization, and that is the notation for the linearization. And then I just want to show you, and I know that they have you kind of do that on some of the other problems, but just to really try to make sure that you understand what you found and how it's helpful. So I know that this is not part of the question that they asked over here. And so this is just a thought. Let's say that you wanted to find the sine of half, 0.5 of half. Now the reason I picked half is that pi over 6 is very close to half. Pi over 6, 3.14 divided by 6 is very, very, very close to half. So what I can do, now let's say that I wanted to find it by hand, right? I don't want to find it using a calculator or a computer or whatever have you. The kind of equipment we have to find the sine of pi over, the sine of 0.5 is all recent. And also, even on computers and whatnot, you want to save computing, their computing speed or their computing memory. I'll have to ask Kevin again what he was saying that they were learning at his school. And this is actually just a lot easier to calculate for a computer because it's just a line. And so you can approximate, this is f at x, f at 0.5. So you can use L of 0.5 to approximate f at 0.5. And so that's the idea, is that I can use this to approximate that thing that I want to find. And that thing that I want to find then, so let's look at it and see if we can find it here, is equal to half. And then this is equal to plus. And this right here, I'm not saying that I'm going to do it by hand right now, but I'm going to tell you that I could do it by hand if I had to. Square root of 6 is around square root of 5, square root of 3, I don't know why I said 6, but the square root of 3 is around 1.73, right? And divide that by 2, I certainly could. And take this, I can divide that 3.14 by 6 by hand, totally by hand, and take as many digits as I want out, subtract that, certainly by hand, multiply this, certainly by hand, and the half, certainly by hand. And when I do that, all by hand, I could do it all by hand, if necessary. And so, and when I do it, I hope that you are putting it in your calculator, although you could do it by hand. I was putting in my calculator, but I was talking at the same time, and then I lost what I was putting in and did not have it going right. So I am going to do better now and try not to talk. So I get this is around 0.479, right? Depending on how far I went when I did it by hand, right? This number actually is a 5, so maybe even 0.48, something along those lines. And then just because we can, I want to compare that. So this compare that, I don't know why I got an L in compare, but I want to compare that to what I got if I was to use my calculator here and found the sine of 0.5. And I said that they were really, really going to be close to one another. Now, I don't know how I would find that by hand at all. There is some ways that you will learn to find the sine by hand in Calc 2. And so I guess maybe from my memory I could come up with that, but no, I'm not going to be able to come up with it right now. But this is 0.5, right? And you notice that the calculator tells me, and look how close it was. I had a 5 here is what I had, but even if I round, totally to the hundreds, totally accurate to the hundreds. And so anyway, and so it's really, really close is my opinion, my story. And this could be done totally by hand with low computer power and whatnot, and this takes more. So that's just kind of some reasons for a linear approximation, that it does give you the same value. And it hasn't been long that there's been calculators. I mean, you guys feel like it's been a long time because like your lifetime it has been. But if you think about Newton and living in the, when did he live? In the 16 somethings, does it say on this paper, when he was doing his rap? I don't know. But, several hundred years ago anyway, we'll go, maybe even more 100 years ago than that. There was no way that this would have made things nicer if you wanted to find something like that, would have made it better. So we're supposed to use linear approximations here to estimate the quantity, the square root of 100.5, and just to see kind of how it would go. And so what we kind of want to do is we want to set up a function that looks like this: f of x equals the square root of x. And then what our idea is going to be is that we're going to use L at 100.5, and that will be, this is an estimate, approximately equal to F at 100.5, right? And so we're going to use this to approximate it. I wonder if I should have that on the other side, because this is my exact value. And so I don't know if that matters. So anyway, in order to do that, you find the tangent line. And so in order to find the tangent line, you have to have the slope. So the slope here is 1 over 2 square root of x. I have just memorized that. So you can do it slowly if you want by hand. The point that would be good, I want to pick a nice point. And the point that I'm going to pick is x is 100. And that was a choice because I want to pick something near that. That is a perfect square, right? So I'm going to have, for my slope of my tangent, I'm going to have 1 over 2 times the square root of 100, which is 1 over 20. And my point, remember you have to know the slope of the tangent line, so it's 1 over 20. And my point is 100, and then you would put that in here to find your y value, which is 10. So we would get y minus y1 equals m times x minus x1. So y minus 10 equals 1 over 20 times x minus 100, right? And y minus 10 equals 1 over 20 minus, that's x, minus 5, right? 5. And then I'm going to add 10. So my tangent line is this. So this is my linear approximation. And I certainly could put any value in there for x and find out what it is very easily, right? And what I'm gonna put in there is L of 100.5. So this is 1 over 20, right, times 100.5 plus 5. And I certainly can long divide that, add 5 to it, all in my little head. And when I do, okay, maybe I'd have to write on paper, maybe even write on the ground, right? But when I do, I get that, is what I get. And again, they're just wanting you, so this, they're saying that this would approximate this, right? And so, and this is equal to the square root of 100.5, right? Which is exactly equal. So this right here is the estimate. And that estimate can be totally done by hand. It doesn't have to take a calculator or a computer. There's not very many people that know how to find a square root by hand. Most Garces students do, because there was someone at Garces that showed people how to do it by hand. And so, but this is exactly 10.024968883, right? That's what it's equal to, and this was our estimate. So you see that's pretty close, right? And so, and this didn't take any, I mean, it took some math, but it didn't take, you know, I didn't have to do it on a computer or whatever. Okay, so that's the idea there. And then differentials, they're showing you differentials, and you're going to do more on differentials in differential equations, which is Math 6D. But they're just kind of showing you some, just right here, just some small ones, not some big ones. And so what they're wanting us to look at here is just so they can, the talk about it is that this delta x right here is the actual change in y. So this is the change in y, and it is the actual change in y, the exact change in y. And for this picture right here, here's my curve, right, y equals f of x here. And they're looking at, for a change in x from this point to this point, there's a change in y. So the change in x might be, you know, that I'm over, you know, 0.01. Well, how much different then is the output for that? And this is the exact value. And I could calculate it if the curve is easy enough to calculate and whatnot. But there's something that you can use, and that's what they're saying. And that thing they're calling dy here. And what that is the approximate change in the y value. And where dy is on here is this value right here, right? And so they're just using the tangent line. They're finding that distance there using the tangent line. And they're kind of saying, well, if you kind of just think about rearranging this, so what is dy equal to? Well, it's equal to the derivative times the change in x is what it's equal to. And this delta x and dx are the same because we know what that change is there. Okay, so we're going to give a try just to some writing first in differential form, and then give a try to this story here. So this was, we had an easy one, y equals 6x plus 2. So if you take the derivative, then dy dx is equal to 6, right? And writing that in differential form is to instead write dy equals 6 times dx. And that is what we had up here, right? dy equals f prime at x dx, right? And so what was that derivative? Well, it was 6, so 6 dx. So it almost just feels like I'm just kind of rearranging this furniture and multiplying that to the other side. And that's what it looks like, and I'm told don't say that, because that's not what you're doing. You're really using this formula here, but that is what it feels like, right? Kind of moving that over. Okay, we have one last question to do, and so delta y, this is the exact value of the change in y, and I realized that I hadn't said that, right? And so delta y, that right there that's what delta y is, and this point right here is f of x plus dx. It's that point right here, right? Because this is x plus delta x. So that point right there, and minus f at x. This was f at x, so that's why that's this height, right? And that's the exact value of delta y. I remember when we were talking about it that I saved that to talk about and then forgot to say, that right there is the exact value, the change in y, the actual value, which is this value right here. Okay, so we're going to draw this step. Well, I'm not going to draw it. I'm going to do it on Desmos, and that's why I had to start the video. I had to stop the video so I could get my Desmos set up so that I could do that. So in part A, they're asking us to find delta y, and that equals f at x plus delta x minus f at x. And so what this is f at, they said 1/3 minus point delta x, right? Minus 0.02 minus f of 1/3. And this is f of f is cosine, right? And so this is the cosine of pi times 1/3 minus 0.02 minus, and then this is just the cosine of 1/3, pi over 3, 1/3 pi, right? So pi times 1/3, 1/3 pi. And so the cosine of 1/3 pi is 0.5. And the cosine of this, well, I don't know, minus 0.5, right? And so I'll use my calculator to find that. So make sure your calculator's in radians. Cosine of pi, and then, gosh, it smells like someone's making cookies. So 0.55. On it goes. Take away 0.5. Right, so I'm going to take away that, and this is going to be left. So however far that you wanted to take that, I decided, I guess, to take that 4 places, 5 places, however many places that is, I can't count. And so that's that story. But I want to show you what we were finding on here, just so that you could kind of see on Desmos. So I had it graph first the cosine of pi x. So there's the graph of the cosine of pi x. Then I asked it to put the first point on there, which is x is 1/3. And if you do then the cosine of 1/3, you get half. So I had it graph that, and it graphed it blue. So there it is, right? And then this is the other point. So 1/3 minus 0.02, you can do that on your calculator, is 47 over 150. So I just want to show you that that is what that is. 1/3 minus 0.02 is 47 over 150. Then I asked it to find the cosine of 47 over 150 pi, which we just found, right? We just found that is this. And I plotted that point, and that point is plotted in green. And then what we're doing is we're finding the difference in the heights, right? And that is what delta y is. So this distance from here to there is delta y. And we found it exactly. Okay, so that's the story there. And then the next thing that they want us to do is that they want us to consider the following function and express the relationship between a small change in x and the corresponding change in y in this form right here, and evaluate dy for the given values of x and dx. So we're going to try that, part B. So they're saying dy equals f prime at x dx, right? And I haven't found the derivative, but let me find the derivative of this. F at x equals cosine of pi x, and I want to write it like that just so that you can see that I have to use the chain rule. I know the derivative of cosine of x, but anything more complicated than that, then I'm going to have to use a rule, right? And so since I have pi x, I'm going to be thinking, well, the outside is cosine of whatever inside I have, and the inside is pi x, so that the derivative is the outside, which is negative sine of pi x, times the derivative of the inside. And a lot of times when I tell people this is pi, they get all upset. But if it had been 2x and I ask you what's the derivative, you'd say 2, right? And so the derivative of pi x is pi. And so this is negative pi sine of pi x, okay? And we are knowing that our x is supposed to be 1/3, right? So this would be equal to, because we're going to put in here 1/3, and so this in here 1/3. So this would be negative pi times the sine of pi over 3 times dx, and dx was given to be negative 0.02. And then I could find this by hand if I had to. I couldn't do that one by hand. But I do know the sine of pi over 3. It's the square root of 3 over 2. Pi is 3.14, right? I can take it 159 if you want, times the square root of 3 over 2, times that. And so I'm not saying that I want to do that by hand. I'm saying I could do that by hand, where I could not do that by hand. There's a difference in wanting to and being able to. So the square root of 3. Oh, I accidentally got in there something else. Over 2. So that's what I get when I estimate it, right? The difference there. And when you estimate it, you're using the tangent line is what you're using. Now, we didn't find the tangent line here, but we certainly could have found the tangent line if we would have wanted, right? And so if you want to do that, you can, and then you can go and you can look, put points on the tangent line and see that this is the difference between the point that it goes right through, which is going to be on the curve, right? Right on the curve was this point here, 1/3, 1/2, and then draw your tangent line, and you'll see, and make it put a dot on it, and you'll see, make a red dot on it if you want to, at where 1/3 is, right? And see that you're just finding that difference, that distance there. So if you wanted to go do that, you definitely could. I'll say that I'm done with the video for people that are not interested, but people who are interested, I think it kind of maybe would be fun. So I'm going to find the tangent line and put it on here. And so only stay tuned if you're willing, if you're thinking it would be fun. So I want to find the tangent line at 1/3, 1/2. So the slope then is the slope of the tangent line. If you put in 1/3, remember that was the square root of 3/2. So this is negative pi times the square root of 3/2 as my slope. What a value, huh? I'm going to write that as negative square root of 3 pi over 2. So my tangent line, y minus half, equals this terrible slope I didn't have to, and then add the half to the other side. So this is really the linear approximation line, isn't it? So that's what I'm gonna call it. Okay, so I'm gonna have it graph that line right here. Y equals, and you can do the same thing too. I'm going to put in half as 0.5 minus fraction square root. So I want square root 3. I want to come out. I want to get pi. I want to divide that by 2, and then I want to have here parentheses x minus 1/3, and I don't want to put in 0.3 because I don't want to start. So are you going to graph that thing? Did you graph it? Yes, you did. You graphed it in red, and you can kind of see that, I guess it's graphed in orange, but it's right on top of the other one, that they're almost the same, right? The curve, that was the curve, and the tangent line are almost the same. And then what we're finding when we use this formula, we're putting in here for x 1/3 minus 0.02, right, in for our x, and we're finding the new output that you would have, which is the same as having 0.02 in here, and then that's what your output would be, right? And you can see, and it will be on the curve, and they're really close together. I mean, they're going to be really close together. So should I do that? Should I put that point on there? I mean, you're like, well, yeah, you went this far. You might as well, right? And so remember that the y value was 47/150. excuse me, the x value. And, oh shoot. Was it this one I wanted to hit? No. Okay, comma. And then I'm going to put in here 1/3 minus 0.02. So when I take away 1/3, I get minus 0.02. So I just want to find out, because I'm going to find this point, 0.5. So I can draw it on there so that I can show you how freaking close these are together. Well, you already know how close they are together. They're really close together, as you can see. But this is what it's doing. And over 2. And this is times negative 0.02. Okay. So 0.55, no decimal point, 0.554413. Of course, I had these numbers before, 9. Okay, so I'm going to put that in there. Did you put it on there in purple? Did you do it? Okay. So then I have now the tangent line on here. I have the tangent line on here, which you can see it there in red. I have the actual from blue to green was actual. And then I have the estimated. Can I turn that off? Purple. And I have the estimated points. I think they're so on top of one another that, oh, I didn't think I had that one drawn. I think they're so on top of one another that you cannot even see the difference between the blue and the purple. Why is that turning off that one? Oh, it should have been the green and the purple are right on top of one another. And are they? If I get rid of it? Yeah, they are. And so anyway, so that's kind of the story on that. And the blue was where I was coming from, right? This is the blue one. That's the blue one. That's both points. You can kind of see both of them on there at one time. Anyway, they're really, really close to one another. So, of course, the distance between the two are very, very similar to one another. Okay, so we did a lot, you know, more than they asked for on that. And so that's it. More than you asked for.